No questions. All right. All right. Let's move on to the next set. Were these examples in the video? I can't remember.
Yes.
Okay, they were. All right. So are there any questions about this? About how we get 7 different types of protons down here, or 7 different types of hydrogen here? Right? Notice there's no symmetry. So everything in this molecule is going to be non-equivalent. So
Yes.
any questions about either of these?
No.
All right. All right. So this, we've seen that NMR. This is what the NMR is going to look like here, right? Where you have 1, 2, 3, 4, 5, 6, 7 signals, right? For this molecule. And then and you can see I highlighted that on purpose. Right? To show like sometimes your signals will overlap. And so you have to be, if you're actually doing NMR, you have to be really careful about determining like where the signals are located, because sometimes you can have signals that overlap. And you have a lot of strange looking splitting here, but that's because that this chlorine is a chiral center. And so the protons adjacent to it are going to give different types of signals. If we get a chance to talk about that, we will. If not, then we may not get a chance to cover it. All right. So let's take this and apply it to a reaction. So let's say we do an allylic bromination reaction, right? And in the allylic I'm sorry, this is HBr addition. Sorry. So let's add HBr to an alkene. This is my product, right? The first question is, how many different types of protons are there in this molecule? How many non-equivalent proton sets are there?
7.
You said 7? So let's see. There's no hydrogens here. So 1, 2, 3, 4, 5. And you're saying that these two are different. Is that right?
Be 6.
Okay. It's either 6 or 7. Is that right? And that's okay. We can go into the example with that uncertainty, because we can look at the example and figure it out. So let's look at it. So let's see. So we have 1, 2, 3, 4, 5, 6 signals. Is that right? What does that mean? If we got 6 signals, but we have seven different proton sets, what does that mean?
The ones connected to BR are equivalent.
Yeah, it means there's some set is equivalent to another set. Is that right? That's a good observation. So when we look at this, we have this black set of protons. I need to fix this slide because it's not supposed to fade out. Not supposed to fade out. Hold up. Let me take this animation off. She straight up hero worshipped the guy when she was a kid. Would have done anything, was willing to travel the world, jump off a cliff, anything to be his daughter. And now plenty of people who just take the blip. So he's not that different, Dallas. Yeah, you would think that Lulu would realize. All right. All right. So now, man, I took the arrows off. So each one of these is going to represent a why is it not? All right. So each one of these protons is representative of one of these signals, and I have them color coded. So you can see the blue protons here or here, right? And then the red protons here. These two CH3s are equivalent, so they're all falling under the same signal. Then the pink protons are here. The TO ones are here. Black is here. And then the orange, or this arrows are yellow, but the orange protons are here, right? So that for that particular molecule, right, this is what the NMR would look like. And so we have 1, 2, 3, 4, 5, 6 different types of non-equivalent protons. And so we're going to see 6 signals in the NMR, right? And then again, the CH3s are identical. They are equivalent, right? And so because of that, they only show up under one signal. All right. Any questions about this compound?
Peak is which element?
Say that again.
Will we have to be able to know which peak is which compound? Like, how will we know that?
You mean which signal corresponds to which type?
Yes.
Oh yeah. We're gonna get to that. We're gonna get to that. There is a way to determine that, and it's actually easier than you think. But there's a way to know which one is which. Let me see what that's the next slide actually. Talking about the multiplicity or the splitting pattern. All right. So if you notice, each one of these signals is not a single line. We already know for ethyl acetate, you're going to have 3 lines, right? 3 signals. So each one of the signals is not a single line, right? And so the way that you determine what's called the splitting pattern or the multiplicity is a simple rule that's called the n+1 rule, right? Very simple. So for the n+1 rule, what I'm looking at, what n is the number of neighboring protons. So n, let's say let's look at these 2 carbons right here, right? This carbon and this carbon. If I'm looking at this set of protons, how many neighboring hydrogens or protons are on the carbon adjacent to it? 3. How many neighboring hydrogens are on oxygen right here? Are there any? None, right? So for this set of protons, let me get this little pen back. For this set of protons, right, n is 3, right? So n+1 is 4. So what that means is that this signal for this set of protons is going to be split into 4 lines, right? That's what that means, that the signal is not going to be just a single line, but it's going to be split into 4 lines, or what we call a quartet, right? Let's look at the blue right here. What about that one? How many neighbors does it have?
2.
2, right here, right? So for that one, let me change the color on that pen. So for this one, n equals 2. So n+1 is 3. Is that right? So what that means is that the signal is going to be split into 3 lines, right? And we'll talk about the names like triplet, quartet, singlet, so on and so forth in a minute. All right. And then what about here? Any neighbors to the left or to the right?
No.
Right. So n is 0. That means n+1 will be 1, right? So that signal is going to be 1 line. Is that okay?
Yeah.
All right. So now let's apply this to the example. And I think this may even answer your question, Taylor, about how do you figure out what's what. There's 2 ways to figure it out. One way is the splitting pattern, and the other way is where it's located. But we haven't talked about that yet. We'll get to that.
Dr. Russell?
Go ahead.
Yeah. I just had a question on why you said that the oxygen didn't have any neighbors, because like those two hydrogens, those aren't adjacent to it on the
Right,
left.
but there's no hydrogens on oxygen.
Okay, got you.
Yeah. So an atom that doesn't have any hydrogens can't split with an atom that's next door to it.
Got you.
And for the most part, oxygen and nitrogen, like heteroatoms, they don't split. Even if they have, like, even if this was an OH group, it still wouldn't split with the neighboring protons.
Okay.
It's really weird, like how some protons are able to split and some aren't. But anytime you have a proton on a heteroatom, like a OH, NH, SH, they won't split. Anyway, even if it was a hydrogen there, it wouldn't split.
Gotcha.
Yeah, good question. All right, so we've already talked about that. So now you can see that this is 4 lines, right? And this is corresponding to this set of protons. And we call that a quartet, right? The CH3 here that has no neighbors, so it's only 1 line. So we call that a singlet. And then the blue protons here, we call that a triplet, right? It has 2 neighbors next door to it, and then n plus, this should be a 3 here, not a 4. But the n plus 1 rule says that this should be split into 3 lines, which we call a triplet. All right. Any questions about the n plus 1 rule? So what we've learned so far is how to determine non-equivalence or equivalence, and then how non-equivalence corresponds to the number of signals, and how the signals split with one another, how the proton signals split with one another. So we learned multiplicity, non-equivalence, and number of signals up to this point. So any questions about anything that we've talked about?
No.
All right. So now let's talk about why, or the location, because that's the other way of determining which proton is which. It's based on location, right? So if you notice, some of these protons are upfield, some of them are downfield, right? This is upfield going this way. I'm just going to abbreviate it because that's upfield, and then this would be downfield. Horrible. All right. So upfield, downfield. And what you'll notice is that the ones that are downfield, the way that we determine whether something is upfield or downfield is based on the environment that it's in. Downfield protons are usually in electron poor environments. Right, so electron poor environments, that's how protons get shifted downfield. That phenomenon or that observation is called deshielding. Right, when a proton is deshielded, the electron density around it is decreased because you have electronegative atoms close by, and so that makes the signal shift downfield. Right, upfield protons are more electron rich. So let's look at the one that's furthest downfield. Right, and if you notice, that corresponds to this set of protons right here that happens to be adjacent to a highly electronegative oxygen atom. Right, oxygen is 3.5 and it's second only to fluorine. And so the fact that this oxygen is here, that's pulling electron density away from the protons, and it's pushing them downfield. All right. this also gives us a rule of thumb too, because a proton that's adjacent to oxygen is normally going to show up in the same region, right? Normally somewhere between 4 and 5 parts per million. There's a chart in this PowerPoint that we'll get to in a second. All right. And then now let's look at the one that's furthest upfield. Notice that corresponds to these protons right here. Right. Now they are close to oxygen, but they're not as close as these. And so that's why there's so much difference between where they're located. Right. So normally on a CH3 or just an alkyl type moiety, those will show up somewhere between 0 and 1. Right. The only reason this is at 1.4 is because it does have this oxygen close to it. But if I added another carbon and pushed this further down the chain, this signal would move further and further upfield, right? The further it got away from oxygen. All right. Any questions about this? And then here, right, you see this signal corresponds to these protons right here. Why do you think that's downfield? If a regular alkyl proton shows up between 0 and 1, why do you think this is downfield?
The carbon arrows take